Heights over Baltimore?
Okay, so the question is, if anyone is learning how to understand the impact of urban heat island on the atmospheric boundary layer, and the answer is yes. Ken, you want to say something?
Well, I would say that courage experiment will nail that. If you measure the boundary layer of the bay in rural Maryland, DC, over Baltimore, all at the same time, 24/7. Because that will have huge impacts on the chemistry. I've seen that chemistry gets really wonky and wrong at nighttime because models can't get that. So I'll love to talk to people. Nick will tell you soon.
Okay, just a brief repetition, and this field campaign is exactly like the answer to the question, and it's a very exciting one. And also a following up question is about that the potential use of this, all the kind of understanding here for the atmospheric chemistry or air pollutant research. And yes, we look forward for that.
Modeling, local kind model, such as sleep.
Okay, so let me repeat the question. The question is about the climate modeling part. So for example, the E3SM, I think the answer to your question is included in this one. No, this one, that we would like to simulate the future conditions. We do have some preliminary work done. We just don't have any presentation at this particular meeting, but we definitely can talk about more details afterwards. I think I have spent a lot of time, so we should move on.
I think it's next.
Yeah.
I've got to change the setting up here to use that, so that's why I'm not. Yeah.
This is yours here, isn't it?
Yeah.
That's mine. And changing slides, just use the mouse or the arrow key.
Yeah. I think both should work.
Yeah.
And the timers are over in that corner.
So. Already 2 minutes left. We'll give the short version 30 seconds or less.
Okay.
All right. So good morning, everyone. Again, my name is Elliot Faust. I'm a doc student in the Penn State Meteorology Department, and I'm working with Ken, Darren, and Ben, at least like on the work I'm presenting here. And so my research tries to tease out answers to the question of whether heat-related mortalities and morbidities are reduced with urban greening. And so I'll jump straight into some of the motivation with this work. And we all know climate change is likely to exacerbate extreme heat. And we know what segments of the population are most vulnerable, especially after the intro that Ying and Darren just gave. But I also want to point out that it's very important that we have a metric to quantify how bad of a hazard that extreme heat is. And one such metric is the excess heat-related deaths. And so this is a useful metric, especially when we try to compare the effectiveness of mitigation strategies. And to illustrate at least one shortcoming of this metric is that there's a lot of uncertainty. And this figure to the right sort of illustrates that. And on the x-axis here is the annual excess heat-related deaths from a study in 2021. And I've cherry-picked 2 cities from the London and Zurich case. And one thing that stands out is, especially for Zurich, that these error bars are very large. And so this is some of the uncertainty with using this metric. And one component of this uncertainty is that it's related to heat exposure. And so one weather station is meant to represent the entire population. But we also know that temperatures are likely to vary within a city. So this is one of these sources of uncertainty. And so now tying this back to BSEC, my goal isn't simply to reproduce this for Baltimore, but essentially we want to develop some of the insights in terms of how do we, one, compress these error bars, and two, how do we implement some mitigation strategies such that we shift these bars to the left, i.e. reducing some of these excess heat-related deaths. And to lay out how I'm going to approach this, the first, I've broken this down into 3 phases, where the first, we want to develop the tool set. And so that's going to consist of both models and observations. And we want to make sure that we validate the model and determine that it performs well over Baltimore. And after that, then we want to assess the spatial and temporal variability. And so that's going to be one of those controlling metrics that helps us to constrain that uncertainty. Then, assuming that we have a capable model, we have a good understanding of the temperature variability, then we can start to implement some mitigation strategies. And just going into some of the tools, you'll probably hear this name a lot, especially over the next talk, WRF, WRF, which is the Weather Research and Forecasting Model. This is kind of like one of the key tools of the trade. And the domain that we're simulating, which Ying just was able to show, all of our data is pretty much coming in this innermost box that's going from Pennsylvania down to DC. And this is at 1 kilometer. So we have a run that we've simulated all of 2021. In addition, we have a suite of sensitivity tests that are listed in this column, where the goal was mainly to change different land cover configurations such that we're playing with different ways to represent the city of Baltimore. And this is for August 2023. And so with that being the model, the obs that we're using come from the Meteorological Assimilation Data Ingest System, or MEDIS, and this is a NOAA product. And these are all ground-based stations that are collecting temperature, relative humidity. Some have precip, wind measurements, and a few other variables. And some of these stations are semi-permanent, mainly the ones like these blue dots that are coming from airports, but these red dots are even crowdsourced stations. One thing, as Darren mentioned, there's a bit of a data gap in Baltimore, so this motivates deploying some of these weather stations, and these are represented by these black dots. Do take a quick note that this is a slightly outdated map since this is from August, but we have deployed more stations since then. And to give a bit of an overview of just how the model's performing and some of the results that we have so far, I'm showing, well, you can't see it, do that label, but that's for this, came up magically, yay. But I'm showing some of the surface the surface fluxes. Reason that we're using the surface fluxes is one of the metrics because it gives us this broader understanding, or more so this fundamental understanding of how the model's performing. And on the top row is the sensible heat flux, and on the bottom row is the latent heat flux. And if you look in this panel in the upper left, where you kind of have this homogeneous blob, where it's kind of showing that urban sensible heat flux is pretty homogeneous. But then as we use some of these other runs, you can kind of see that starting to dissolve a little bit. And so that becomes an issue where we want to utilize the flux towers to be able to validate this. So which one of these is performing most realistic? And kind of to jump to the case, like jump to the end, especially with the evaluation. One thing that we've noticed that models perform in some cases similarly, sometimes we see large differences. At least during the daytime, these orange boxes are showing the 2-meter temperature. A lot of the models seem to perform well during the daytime, at least for 2-meter temperature, but a lot of them also underestimate heat stress or the heat index. And we do see different results from daytime and nighttime. But to jump to the chase, we have determined that this case called NLCD with the mosaic has been the most robust. It doesn't perform best all the time, but it has been shown to be the best overall. And so that's what we want to use going forward with all of our models, with all of our modeling configurations. So that was pretty much the performance of the model. And looking at OBS, well, I have the model here. This is the mean 2-meter temperature, and this plot is showing the MEDIS stations. And what's interesting on this plot is that it shows the variability, the mesoscale variability, which is this shading. So this is a Kriging, which is basically a way of interpolating all of these observations. You can see this background pattern. But then on top of that is some variability showing from microclimates and/or the stations themselves. And one thing I do want to point out of note is that you can kind of compare this model with this background shading. And we see that the model's performing pretty well, getting this pattern. And one thing that stood out was this area south of Baltimore was extremely warm. And it's even warmer than the city center. And initially that looked weird. Like, why does the model do that? But then we see that that's kind of consistent here with the observations. So this might be a real phenomenon that warrants more investigation. And just this is more so a preview of kind of what's to come. So now that we know that the model, we're starting to work with the model, seeing how it performs spatially, but this is just a little preview of a case where we tried to remove the urbanization in a city. So throughout the domain, we replaced all development with basically an open space, basically created a park everywhere. And we see that we get a lot of cooling throughout this whole domain, just about 1.5 degrees C. And so that begs the question for the research is, say 1.5 C, does that have a big effect on heat-related mortality, especially during a heat wave? And then when we implement something more realistic, this number may be 1 C, maybe 2 C. Does that also have that same impact? And just going forward, I will start writing some of this stuff up, and Winter will start running these mitigation scenarios, but also looking for other collaborations, especially to help tie this down.
Questions? One right at the back.
So when you're looking, it looks like you're a little bit far away from looking at mortality. One thing that's going to affect mortality is the age composition of neighborhoods. So I'm wondering if you looked at you started thinking about where the cooling is happening relative to the age composition of the neighborhoods that would lead to mortality.
Yep. So this has been kind of like in the back of our minds to some degree.
Just briefly repeat the question.
And do I repeat it loud or do I need?
No,
It's a bit loud. The question was, have we thought about, especially age and location of where these heat-related mortalities may occur? And so that's something that's been in the back of our mind. And what makes that a real difficult challenge is, especially when we try to use the mortality data sets, that generally gets aggregated just to protect privacy. So we won't I can't confirm whether we'll be able to utilize something at that scale. So we may have something like, it may go to county level, may go something a little bit finer to that. So once we get a better handle on that, then we'll be able to tease it.
But your model should be able to put the input to someone who could test it.
Mm-hmm.
When you run and compare, the say, Modus with NLCD, running this in a mosaic mode, and then each more so that across the distribution left coverage or using that to get all the effective parameters over more grid related for the LP.
So the question was about some of the land cover schemes that we're using, especially with comparing Mosaic and Modus and NLCD and whether we're applying the Mosaic to it. And so we've done kind of a little bit of a mix of both, because from previous studies, we've looked at USGS or Modus in bulk and compared that to different mosaics, and we kind of knew how that behaves. And so for the subsequent runs, we've pretty much been using the Mosaic by default since then.
Okay, thanks, Elliot. We're gonna move on.
Hey, Darren, you mind if I pilot?
Was there a question?
Yeah, you mind if I pilot?
Oh, yeah. Sorry, I didn't know you were remote.
No, you're okay. Yeah.
That's why I couldn't see you in the room.
Makes sense. Okay, let's see. Can you see this?
Yep. Yep. Let me. How do I do? Yep. Carry on.
Okay. So I'm just going to carry on from what Elliot was just talking about, right? So we're going to keep looking at WRF. But now essentially what we're going to do is we're going to utilize something called WRF LES, where we're going to, as Ying said prior, continue to dynamically downscale until we get into around the tens of meter scale. So we're getting at neighborhood resolution here. And we kind of want to look to see if we actually need to get to this scale in order to represent certain heterogeneities that exist across the environment. So let's get into it a little bit. See if I can go forward. There we go. So here's some of the scientific questions that I have, and I think a lot of the BSEC folks generally have as well, when we're trying to actually advance these models to better guide equitable pathways, right? So do we need a fine resolution to capture these neighborhood heterogeneities, right? So running this model is really somewhat expensive. As Ying will tell you, we like to choke the computer, right? Elliot running at 1 kilometer resolution is much nicer. We can do that for an entire year, multiple years. When I'm running something like this, I can really only target a very small time period, roughly a few days here. So do we need to go to this resolution, this really fine resolution? How well are we able to capture these heterogeneities that might exist? And maybe what aspects of the environment do we struggle to simulate, and how might we better improve the simulation of these aspects? Some of the research connections to you guys that you might have too, right? Because I'm not here just to answer my questions. I'm here to try and address these great questions that people in the room are coming up with as well, right? So we can get things like turbulent transport of atmospheric constituents here. We're actually resolving the turbulent motions here, at least the most important ones, as Ying said. We can use it at forcing for other models. Again, fine resolution to simulate key areas of interest. If somebody has an area that they're like, wow, it'd be really nice to get the actual atmospheric flow, turbulence and all over X area, we can do that with this. So again, here's Elliot's domain, going down to 1 kilometer, nesting here. I'm going to continue to downscale this to further, to keep going down and to get to neighborhood scale. So this is kind of what it looks like here. So I'm blowing up the 4th, the 5th, and the 6th domain, which I've nested inside that 5th or that 3rd domain. Once I go from the 3rd domain to the 4th domain, I'm turning on something called the LES, where we begin to resolve the turbulent motions. You can see here, I'm targeting this area, which encompasses Broadway East, Clifton Park, and the cemetery there as well. And I'm going down 37 meters here. So here's this blown up even more, right? So this is, you can see there's a lot of heterogeneities that exist across this scale, right? Now, what do those look like? Oh, and there's the flux tower. So a lot of my questions are going to revolve around this flux tower, but right, we're not just trying to use the flux tower data. We've got all this other great data that we can implement in this MUDX framework to try and get at how well we're able to represent this environment. But before we go any further, how much heterogeneity is there? So what I'm going to do is I'm going to pop a Landsat image of skin surface temperature over my domain here for a certain period in the middle of the afternoon in, I think it was June. Yeah, June 30th, 2021, around noon. So you can see we got a lot of heterogeneity here. We can see the park much cooler than the surrounding environment. And when you're thinking of skin surface temperature, this is literally like if you took your shoes off and you stepped on the surface, how hot or cool that surface is. So you can see, as you would think, the park, the cemetery, much cooler than the surrounding urban environment. So what does that look like now in the 1 kilometer wharf case? Oh, and I should also point out there's a 13-degree difference between these two areas, right? So there is a lot of heterogeneity here. This is what it looks like in wharf at 1 kilometer. You can see we're not, and this is the same scale temperature. You can see we're not really getting a lot of variability here. You can see a little bit of actual warmer here around the park, which is in contrast to what we just saw in the Landsat image. So, okay, something seems to be strange there. Now, this is what it looks like in the LAS. When you break it out in the LAS, you can see, okay, we're actually starting to resolve some of these differences, but now we're doing it backwards. We've got these parks that are warmer than the surrounding area, and that's not quite right based on what we just saw in this Landsat image. And again, I'm showing right now skin surface temperature, but this could be applied to just about any environmental variable that we're interested in. I'm just using skin surface temperature as an example because, you know, it's a very important variable for heat-related stress and things of that nature. So we've got this difference between models and obs where we're overestimating these green areas, much too warm, and we're drastically underestimating the surrounding urban environment. So really quick, how could we do something to fix this? What I'm going to do, like one thing at a time, I thought, well, these hot parks are a bit of a problem. So I went into the modeling framework, very simple. There's a parameter, there's a set of parameters representing the land use for those parks. and looking at them, they weren't necessarily realistic, what I would consider for an actual park. So I switched them out with actual parameters that represent like a grass field. And you can see what that did is it actually cooled down that whole area. Now, it is roughly the same temperature as the surrounding environment, and these are clouds right here. So you're actually resolving clouds here, which is kind of nice. So this is clouds impeding short wave radiation, making that area cooler. But you can see our park is now cooler, which is really nice. Didn't necessarily obviously address our too cool urban surrounding, but our park's a little bit. Now, what does that look like compared to Landsat? You can see we've got a slight cold bias, but this is only about a degree or less than a degree. So now we're actually getting better representation of this park skin surface temperature simply by switching out the parameters set. So that's the whole basis here, right? We've got this whole suite of awesome measurements that we're collecting and that the community partners are collecting out in the neighborhood like Broadway East. And we want to use those measurements to then probe the model, see where its shortcomings exist, and potentially essentially advance the model and try and better how those are represented in the model's framework, right? So that's that, and then use those to then address some of the questions that our community partners might have. So again, this is not about my questions necessarily. We've got this really powerful tool here where we could potentially answer other folks' questions if they could see a use for this like high resolution simulation as like tens of meters scale. Anyway, so that's all I've got. I'm going to keep it nice and short and sweet, and I'll take any questions.
Thanks, Jackson.
Yep.
We have questions? Yep, there's one at the back. Keep it simple because I'm going to have to translate it.
Thanks. The LAS will resolve the advection of heat across different types of surfaces. So you show your parks relative to the hardscape, and depending on wind direction, of course, can you just expect what the adjustment is, but the advection.
Did you hear that, Jason?
I heard advection, and I think I heard it. Like, let me see.
Okay, so the question is whether whether the model will include the effective advection over different land surfaces.
Absolutely. So as far as like one column of Earth to another, no, I don't think so. So not actual like lateral transport of heat subsurface, but above the atmospheric transport of the flow will advect heat, will advect moisture, of all these things. So you're actually, you're getting advection above surface.
Is there an edge effect that you could see?
Is there an edge effect?
Yeah, there's definitely an edge effect. Yeah. Now, how well does it capture the edge effect, Larry? That's a whole different question.
This is the way to try to do it.
Yeah. Okay.
I'm going to stop sharing.
Okay. Thanks, Jason.
Yep. Thank you, guys. Wish I could be there.
So is Nick online as well? Okay.
Yes, sir.
So you take control.
You got it.
Stick where? So I should say, as you can tell, we're not doing a very good job of introducing the speakers. So we're leaving it up to yourself just to introduce who you are. So, well, this is Nick. Take it away.
Okay. Hi, everyone. I'm Nick Prince. I work with Ken, looking into right now the mesoscale influences on the boundary layer characteristics over and around Baltimore, the whole region. So we're not just interested in what's going on in the city, but the neighboring regions around the city as well. We'll talk about why that's important. So just a really quick introduction of the boundary layer. You've probably seen the word already a few times. Just bare bones definition from the age-old texts. The atmospheric boundary layer is the lowest part of the atmosphere, directly influenced by the Earth's surface. Over here on the right, you can see a daily cycle of the boundary layer structure. The most well-studied part of the structure is the convective mixed boundary layer during the daytime, but we'll be interested in looking at this across all times, not just the morning, or rather, sorry, the afternoon. And why do we even care about looking at the boundary layer? Well, within the boundary layer exists the turbulent dynamics in the atmosphere that drive the exchange of mass, energy, and momentum between the Earth's surface and the overlying free atmosphere. So basically anything that originates near the surface has to go through the boundary layer to get higher up in the atmosphere. That's pretty sensible. Why do we care? Well, the boundary layer is pervasive in all weather phenomena, it feels like. And I've labeled a few feedbacks, and I like to call them feedbacks because the boundary layer both impacts and is impacted by these different things. And I think somebody mentioned the urban heat island earlier. But here are some other ones as well. We have weather patterns, such as storms. These can impact boundary layer, the structure of the boundary layer. And both the structure of the boundary layer can either make or break a storm. We have local climate phenomenon, including droughts and heat waves. The boundary layer can serve to exacerbate or mitigate these certain local scale climate features. And air pollution dispersion, of course, this is the boundary layer's bread and butter. It distributes the pollution in the atmosphere near the surface equally and serves to dilute it even. And finally, the urban heat island, which is the one we'll be most interested in. If you're trapping a bunch of heat in the urban corridor, this of course is going to have an impact on the dynamics, and then further things such as, I think somebody mentioned, the chemistry even. So what I'm interested in is not just what's going on in the city, but the large scale environment surrounding the city. I like to say that Baltimore does not live in isolation. It too lives within a larger atmosphere, and exactly understanding what large scale features are impacting the local city, I think will be important for determining how to allocate resources effectively for mitigating things like heat waves. So just a few examples of some mesoscale dynamics. We have regional scale circulations. Basically, if you get a gradient in some variable, you're gonna get a circulation around that. And the two I have listed here are the urban heat island circulation. This is the importation of cool air into the city during the afternoon, or in the evening, I should say, this after sunset, due to the differential cooling between the urban corridor and the rural sector. And then we have also the bay breeze, and that is kind of the opposite. It's the differential heating during the daytime that causes the circulation from the bay into the city, bringing in moist air. So exactly how these will impact the boundary layer structure, and by boundary layer structure, I mean things like its depth and the turbulence that exists within it. And exactly knowing how these circulations are going to impact the boundary layer remain to some extent unknown. And then just general advection of these quantities in the atmosphere, right? You have a city that's generating a bunch of heat. Well, eventually, I mean, the atmosphere is not always stagnant. That heat will be transported downwind, impacting things like rural regions and the surrounding area. And this can actually have an impact on crop production. And so mitigating heat within the city is not just beneficial for the city, but also the surrounding region. And vice versa, if you have another city, say Washington, D.C. to the southwest, and its heat is being advected into the city, there's not much Baltimore can do if the heat is generated elsewhere and imported in. So just some examples of the impact of advection. Just a real brief study design. I'm not going to go too much in detail here. On the left there, you have the LiDAR that you saw earlier. But that's really the focus of this study, is that instrument. We're going to make observations of the boundary layer structure using LiDAR and obviously a myriad of other instruments. We're going to model the atmosphere at the 1 kilometer scale using WRF, as Elliot had shown. And then we're going to match them and see what tweaks can we make to the model, and really understand the shortcomings of the model that is leading it to not produce the correct results to begin with. That's the research aspect of this. And then compare it. And we're going to integrate some of the results or sorry, some of the data from the Courage deployment that is coming up to look at not just the city, but also the rural region to the west, northwest, and even the bay, the marine region as well. So we'll have a very clear understanding of not just in the city, but the surrounding region as well. Some of the questions I hope to answer include simply, do regional scale dynamics impact the urban boundary layer state? That's very simple. Do they even impact it? And some of the things we'll be looking at, boundary layer depth, turbulence, and cloud formation are going to be some of the main hitters. And by cloud formation, I mean boundary layer clouds, not like top of the atmosphere type clouds. And the expected outcomes to identify when and where regional scale dynamics are going to play that integral part in impacting the Baltimore's local environment so that resources can be better allocated during those time periods. All right, into the observations here. So right now we have a Doppler LiDAR stationed at Morgan State University. I don't think it's a secret now, but unfortunately it's currently under repair. I wanted to be transparent. I could have hit it, but I decided to bring it to you. So it's in repair right now, so don't go out there looking for it. But we also, in addition to that, we have auxiliary measurements to go along with that, including weather balloons being launched weekly at Morgan State University. You can really quickly see a couple of those images right there. I'll go a little bit more in depth in them in a second. If you're interested in looking up the LiDAR data, I handle it personally and it's on MSD Live. If you find any errors, please let me know. That way we can make a great data set. What does the LiDAR give you? I think this is what people are interested in. And so I'm going to tell you. Here are the three primary variables that come from the LiDAR. The number one is simply the signal. That's the brown color, or tan even. Lighter tan indicates a greater return signal, and closer to black indicates no signal at all. And then we have the second one. This is the aerosol backscatter. And so where red colors indicate either A, higher concentration of air pollutants in the air, or B, larger particles. It can mean either or. And there's reasons for that, but just know it means one or the other. And you can even see here up at near the top on the right side, I don't know if you can see my mouse, might be able to.
You can.
Oh, great, thank you. But up here at the top, we have these clouds. So these are little boundary layer clouds. And the most interesting part is the third panel. This is what brings, this is what puts the DOP in Doppler. I don't know if that's a saying, but you can see here, this is actually the velocity moving away and towards from the LiDAR. So since our LiDAR is pointing up, that means air that is moving up versus air that is moving down. So red air is moving up, blue air is moving down. And you can see here very clearly the turbulence generated during the daytime in this region right here that is owing to the development of these clouds up here. And so these different things will obviously have an impact on the environment during that time. If you actually want to get into more, you can even look at this is the vertical velocity variance, which is effectively a measure of the turbulent kinetic energy of the boundary layer, where the brighter yellow indicates a lot more turbulence and the darker blue indicates little to no turbulence. And so in this picture here, you can see all of the thermal and all of the vertical velocity that we saw in the afternoon is owing to a lot of turbulent kinetic in the energy, which is driving that exchange that I talked about at the beginning. And thirdly, we have horizontal wind profiles. So this is a very messy graph, but this is one of the aspects, the nice aspects of the LiDAR is we get a horizontal wind profile every 15 minutes from the LiDAR. And it can help you point out interesting features. On this day, I got lucky and actually managed to capture this morning or nighttime low-level jets. You can see this is all the way up to 20 meters per second in the morning here and around 400 meters. So you can point out interesting features such as the low-level jet that will further impact the environment in that region. So you get a whole profile. You don't just get it at one point. So it's kind of nice. Next steps, right now I'm working on still developing the code for retrieving boundary layer depth. It's almost there. I didn't feel comfortable bringing it here. Cloud base height, that's pretty much done. So if you want to know the base of the clouds, you can use the LiDAR to do that. Cloud fraction, that comes with the cloud base height effectively. And the turbulence we just saw. So a lot of this is underway or all effectively done. And then working on the model aspect of this, looking for comparison. So just some last sentences. Boundary layer dynamics, they govern many facets of the urban environments, but they're often impacted by environmental conditions beyond what is taking place in the urban area. It also has to take into consider the large scale advection. And in order to accurately predict the atmosphere within the urban environment, I think taking these dynamics into consideration will be vital. And so I think that's all I got. Hopefully I'm not too long over time.
Thanks, Nick. Time for one quick question. Yep, Ben.
For the weekly weather sun launches, how closely or when do they correspond to the daily weather sun launches that happen around the area?
The question was the launches, the sun launches from Morgan State, are they coordinated in any way with or close to the sun launches that come in the area, which I guess is in Sterling, Virginia is where they are. Do you know if the Nick, do you know if they're at the same time as the weather service ones?
I don't think we're doing it at the same time as the weather service ones. We're doing it a little earlier, I think around 3 o'clock. So I think we tried to aim for middle of the convective boundary layer, whereas the weather people, they put it at, I think, around 6 or something around there. And so, which is a little bit later in the day and not as ideal, I think.
Okay, for the sake of time, we're going to move on. Thanks, Nick. I think the next talk's remote as well. Nick, can you stop sharing? And Dad, are you on?
Yes, can you hear me?
Yep. So you should
Awesome. Okay, just give me a
Remember-
second.
remember to do your self-introduction.
So can you see my screen?
Yep, that's great. Take it away.
Awesome. Hello, everyone. My name is Mahda Talipur. I'm a postdoctoral fellow at Johns Hopkins, working with Ben and Darren for the past 2 years on the same on the BSEC project. Today, I'm going to present a part of my postdoc work at fine scale WRF-LES simulations on urban heat island effect, which basically stemmed from my PhD work. And most of the slides here are actually based on a study that I have under review right now, working with also Claire and Ellie, my PhD advisors. Okay. So the overarching goal of my study for the BSEC has been to evaluate mitigation scenarios at fine scales to reduce Baltimore heat island effect. With that goal in mind, as part of my PhD, I wanted to first evaluate the applicability of WRF in large eddy simulation mode with urban canopy models. In simulation of urban heat island at fine scale. Up to that point, we were not aware of many studies that had done simulations of urban heat island at that fine scale using WRF-LES. So basically, the second goal was to evaluate and conduct a sensitivity analysis to see how sensitive is WRF-LES to soil moisture spin-out, to soil moisture interpolation, and land surface parameterization like mosaic approach. And then finally, the goal was to, after we come up with this sensitivity analysis and evaluate this. So then finally, the goal was to investigate various mitigation scenarios using WRF-Elias UCM. So far, we have carried out the first two objectives, and the third objective is underway. So from the beginning, I should mention, so okay, so here are the nested domains I used for the sensitivity analysis domain. So I have 5 domains, and the blue domain 5, is basically what I use for the sensitivity analysis part of this study. Although the final domain, which I'm gonna use for the mitigation scenario, is gonna sit under, in that it's gonna be domain 6, which is smaller and is focused only on Baltimore. And the resolution is either 30 or 50 meters, so depending on the further discussions. But here on the left, you can see the configurations of the domain, and here is actually the domain that I used for the sensitivity analysis. So the resolution was 150 meter, and the extent was 97.2 kilometer by 97.2 in the horizontal direction. The number of grid points 648, and for the domain 5, for the sensitivity analysis, the vertical layers were 75. So just for the time, we're gonna skip that. So the analysis time that I used was August 22nd, 2017 at noon. And I specifically chose that time because we had a clear sky Landsat observation of LSD over Baltimore, and it was during a heat wave, or kind of. So I wanted to focus that to see if the model is actually able to capture the urban to rural heat gradient, and also the urban heat island effect. So basically, I'm presenting 9 scenarios out of 20 different kind of scenarios that I designed to conduct sensitivity analysis of WRF-Elias to different kind of parameterization. So I use different urban canopy models, not shown here, and other kind of methods for parameterization and initialization of soil moisture and other parameters. But here, the focus on 3 different groups. So I had and mostly focused on soil moisture. So I had the original group, which used basically, like many studies, used the original soil moisture coming up from NAR, which is a reanalysis run at very low resolutions. And the mosaic was using the same input, but I wanted to see if the mosaic approach, because as Elliot also shown, mosaic has shown to be very effective at subsurface parameterizations and used before, but I wanted to see if it is applicable to to higher resolution as well. And the last group was an interpolated group, which basically I used an interpolation scheme because the innermost domain 4 and 5, our earliest domain, we could not afford to run them for the entire period of spin-off. So they were running like most WRF-Elias a couple of days before the analysis time. So the interpolated scheme basically used the soil moisture that was spun up already by the parent domains, which are like domain 3, 2, 1. So those were the 3 main group, and I had 3 different starting time because, like I said, there were no consensus because there were not many studies running WRF-Elias at that time. Actually, we were not aware of any study at that time that had done WRF-Elias at that resolution, evaluating against any observation. So there were no consensus on how much time we should spin up the domain, spin up the simulation. So I used 3 different starting points, one from August 17, almost 2 weeks before the analysis period, August 14, and August 17. And I had it across these 3 different groups. So here I of course picked the best scenario performance. I mean, there was not much of a difference between all of the scenarios, but of course, the 17 group had the highest difference, but this is just showing the spatial difference. Overall, we were satisfied with the performance of WRF-LES in capturing first the urban heat island effect, and also the gradient of rural to urban temperature. However, as you can see from my mouse, so this is the Landsat, and we could see that WRF-LES could not capture the highest temperature in, land surface temperature in the urban areas, as is shown in Landsat. And also there were some discrepancy over here that the model were not be able to capture. Next, this is just, I'm gonna skip through this quickly, but these were the comparison of all the models. I look at the Taylor diagram and also the Bayes and error diagram to just compare different scenarios and see how do they perform compared to Landsat statistically. So it turned out the simulation period, the spin-up period, had the higher effect, and actually it resulted in larger biases and errors compared to Landsat. And also the interpolation scheme did help with some of the surface fluxes and land surface temperature prediction, which are the red ones. And this is like the interpolated one with the longest spin-up period. Also, I checked the air temperature, 2-meter air temperature data at multiple stations, just showing 3 of them here. I think there were 8 of them across the domain, which I checked the 2-meter air temperature and compared it to the scenarios. And overall, the performance of air temperature was satisfactory, but there were some discrepancies, specifically near the bay, which is not shown here, but we thought that it's because of the bay temperature ingested into the simulation from the beginning. One last thing. So for the ASOS temperature, we didn't have like many data set as Elliot and others mentioned in the team. But so I was fortunate that my simulations were at the same time at Darren and Ben had IWA10 data set across the Baltimore. So I compared my simulation results. These are 2-meter air temperature, which I'm just looking at the T-mean right now, T-minimum. But so it was across different land covers. One thing that was interesting, I saw the same pattern that I saw in the land surface temperature in air temperature as well, which the model was not able to capture the variation in the urban area. So from different land covers, high density areas to low density areas. So with that, the conclusion was that soil moisture initially strongly influences models' performance, and also we probably need further parameterization and modification in WRF if we are going to capture the high density urban areas. This is something that I've been discussing with my PhD co-advisor Eli Buzaid for the next step of the project. As I showed, all scenarios did not capture the high AT and high temperature, both air and land surface in high intensity urban areas. And next, after I'm done with this, we are going to run mitigation scenarios using the same kind of setup, same nested, but I'm going to introduce the sixth domain, which I already had the par flow simulation ready to fit in for the soil moisture part. With that, I would be happy to answer any questions.
Thank you. Do we have any questions? Hope it's, yep, when King
See.
I'll hear you this.
Yeah, Madad, it's intriguing that both you and Jason seem to show a lack of ability to get the hot city, and I think Elliot has seen some of the same thing. We're guessing it's the land surface model parameters. What are your thoughts there?
I think it's the urban canopy models. I think they were not probably designed. We had a long discussion with Dan Lee to be run at those fine resolutions. There were there was a back and forth discussion between Ellie, Dan, and I. Dan is also a collaborator on this paper. So we mostly think it's coming from the urban canopy model, although I should mention, so I specifically used version 3.9 because I wanted to use to run it with par flow in fully coupled mode. So in next version of SLUSM, I had been in discussion with the postdoc working with Fei Chen, and they had made some huge improvements in recent versions of WRF in the urban canopy model. I'm not sure if those have been tested by Jason or Elliot, but I haven't tested them myself. But apparently, as I think his name is, I hope I'm not butchering his name, but Chen Lin from NCAR, he basically said that WoodApp probably address some of these issues.
Yeah, WoodApp actually looks worse than Elliot's runs.
Oh, okay.
We should stay in touch and try to coordinate on this because we got the best data set I think we could get to test these things.
Great. Awesome.
Sorry if I missed this. I'm just curious, how long are you allowing for the soil moisture to spin up?
So the question is, how long are you allowing the soil moisture to spin up?
Okay, so for different scenarios, I had 14, 7 days, and 4 days before the analysis period. Of course, the 4 days was the worst. In terms of air temperature, having 7 days showed the most reasonable performance, both for air temperature and land surface temperature. But using the interpolated scheme also helped with the longer 14 days spin-up period.
Okay, thanks a lot. We've got a few minutes. We could have discussion or we could have a longer coffee break. I'm not even going to vote. We can take a longer coffee break. So we're back at 11.
Hi, this is Israel. May I ask a question before we break into the coffee? So I was wondering, are these simulations done for the same heat wave, yours and Jason?
No, no. So we should, the question was the two simulations for different time periods. So we should do some coordination there to see if we can simulate the same time period.
We are not yet coordinated in that way, Israel.
Yeah.
But they are both focused on a heat wave, or
yes, but heat waves, but from different years.
Okay.
Yeah, the curse, Israel, is the data sets keep advancing, so you're always tempted to get the more recent time when you have more data.
Yeah.
But we need to settle at some point.
Okay, coffee break. Be back in the room before 11. So we can start on 11.
You could help us focus on some mid periods at some point, Israel. It's a good idea.
So what's happening here? Good, good.
Are you emceeing all day?
Yeah,
So I have a request to make.
Yeah,
If people haven't done their bios, they should get hold of me and we can schedule a time to make that happen.
okay,
And I will be here today. I will be here tomorrow. I may even be able to have some of those conversations today, but I also like to
okay,
schedule them.
okay, great.
Thank you.
Get you to put your hand up. Okay, yeah. Why?
My kids can't start. I can get them there. I got here today at 9. If we can swap.
Okay. Yeah, let's agree. See if I can do that.
Pretty good.
Yeah.
And Demetrius traveling otherwise.
Yeah. No.
Well, you can do better than this.
A few seconds.
Yeah, then I'd say let's just get going. Because right.
Okay, thanks for coming back on time. Before I hand it over to the Buildings and Energy Group, Miriam, you wanna?
Oh, yeah. So I'm Mary Evans. I'm doing writing and editing with USAC. And one of the things I've been asked to do is to prepare bios for the website that don't have jargon. So I'm not using words like hydrology. If you've already worked with me, thank you. If you have not worked with me to get your bio up, or if it's kind of in the middle of it, please find me. We'll schedule a time to make it happen. Find me. I'll be here today and tomorrow. Thanks.
Any other announcements? Nope, okay, take it away.
Thank you so much. Hello, everyone, and good morning. My name is Rahman Azaria, and I'm an associate professor of architecture at Penn State, and I represent buildings and energy theme today. So why research on buildings? The main reason is that out of almost 100 quadrillion BTU of energy that we consume in the United States every year, almost 39% of that goes into buildings operation, 21% into residential buildings, almost 18% into commercial buildings, and that is primarily used for heating buildings, cooling buildings, lighting, equipment, etc. So with that reason for doing research on buildings, the main goals and investigations that we are currently working on in buildings and energy theme is what are the long-term effects of increased urban density on the energy consumption at the urban level? What is the long-term effects of retrofitting on the urban building energy consumption and carbon emissions? What are the potentials of renewable energy integration and demand flexibility for power grid? And what are part of our research is also on energy poverty and what the determinants of energy poverty in Baltimore. And the type of approaches that we use in buildings and the energy theme ranges from energy simulation at building scale and urban scale to a statistical analysis. And then we will use different tools for those. So,
gotta remember to share the slides on Zoom.
oh, my apologies, I should have done.
You're online and we could get to share the slides, please yell out.
Yes. And the only, I think, challenge now is that I can't do it in full view. Let me see. Full screen mode. Is everyone able to see this on Zoom?
Okay, hello, Amanda. So.
Yep, looks good.
Okay, very good. Thank you. So we have currently 6 projects in buildings and energy theme, 4 of which will be presented today in this session, and 2 of which will be presented tomorrow in greenhouse gas emissions talks. In the first project that we will talk about today, Arjun Janardhanan will share his research on drivers of energy burden in Baltimore and energy poverty in Baltimore. Energy burden is the percentage of income that goes, that is spent on utility bills. And Arjun will share his research on that with us. In the second presentation, Rosina Adhikari will share her research about development of representative energy models for row houses in Baltimore and how retrofitting of those row houses could impact the energy consumption in city. In the third project, Rawat El-Kontar will share his research about the framework for characterizing bottom-up urban energy models. For building good energy models, we need to have good models for to represent buildings and neighborhoods. So Rawat will share his research about how we could build better characterization models for building stock in order to build better energy models at urban scale. And in the last presentation of this session, Alex Nwuso from Oregon State University will share his research about impact of green buildings in Baltimore and some of the distributions of the green buildings in Baltimore, and he will compare it with Washington, D.C.'s green buildings. So if there's any research, any question, I would be happy to answer. If not, we would proceed into first presentation. All right, well, thank you so much, and Arjun.
Will you share the whole, rather than the presentation, share the whole screen?
Yes, I'm sharing the whole screen now. And you want to fill up or you would let me?
I can. Oh, yeah. My name is Arjun KJ. I'm from Penn State. I recently graduated with a master's science degree in architecture and sustainability cluster. I work with Rahman, Lisa. These are the labs I'm associated with. So I'll be talking about energy poverty. Energy poverty is simply defined as the inability. Okay. There's problems with Google Slides and presentation. I think PowerPoint is not picking up Google Slides, so it's a little bit jumbled. So yeah, again, energy poverty is defined as the inability of an household to meet basic energy requirements such as cooking, heating, lighting, etc. And these are the data from 2020. We can see that energy poverty differs from each social group and also geographical locations. So you tend to see energy poverty more in eastern, like older cities. And if you look at the socio-economic groups, lower income groups and racial minorities have energy poverty much higher than the national average. The 3.1 you see here is the national average at the time. And you can see that a lot of these socio-economic groups are have energy poverty much higher than the national average. And also one thing to keep in mind is that energy burden is a metric which we use to quantify energy poverty. There are other metrics as well, but energy burden is very simple and it's used, mostly. And 6% is the threshold. that we have to consider whether they're energy poor or not. So you can see that all these households have something around about 9, which is much higher than the threshold. And also we have to understand that energy is not just a technical thing, it's a mixture of social cultural factors, which is often underlooked when we talk about science and theory. So the inequalities in the socio-cultural sphere will affect the inequalities in energy consumption, energy distribution. So to talk more about energy poverty is a it's a multifaceted problem. It can affect individual development, health condition, learning factors in children. And many of the energy poverty homes will result in health outcomes, like it will impact the health of the people living in cold homes for a longer time, can have respiratory issues. So without mitigating measures, this goes on over time, and households go down in the socioeconomic ladder. So it becomes like a spiral which brings you down, pulls you down, like as time moves on, if you don't do anything about it. So that makes energy poverty a very unique form of poverty due to its material connection with your housing quality and your income level, with all these factors, which makes energy poverty very distinct. And Baltimore is one of the cities which have high levels of energy poverty, especially in lower income groups. As I stated before, national average is around 3.1. Lower income groups in Baltimore have something around 19 energy burden level. And these are mappings of Baltimore. This is homeowners loan corporation zoning of residential security in 1937, also called a redlining map. And this is 2020 energy burden clusters. So the red thing that you see, the spatial cluster of energy burden homes. And you can see that it aligns with the blight concentration in 1964. So blight is basically houses or neighborhoods which are low in have detrimental physical aspects and socioeconomic factors. So these dots that you see is high of blight concentration that aligns with these spatial clusters. And the yellow that you see is the gentrified census tracts, which have been seen from 2000 to 2013. And you can see the cold spot, which is in blue, which was affected by blight, was gentrified, and it was blue color. So gentrification may have driven out the lower income groups into other neighborhoods. That's why average energy burden could be low in those areas. But however, these highlighted spots have significantly high cluster of energy burden. So these are the research questions I have. What are the spatial drivers of energy burden in Baltimore City, and how does it vary spatially? So based on literature, we identified 4 important groups. The first one is socioeconomic, and second one is socio-demographic. And socioeconomic and socio-demographic, these are social aspects such as household income, median rent, education level, and unemployment rate, single parents. So all these social aspects come in those category. And urban and environmental factors, and urban and architecture in this factor is more material and spatial. So it's like renter occupancy, built year, architecture quality, percentage of multifamily housing, etc. Yeah. So based on statistical reduction, we identified 7 important factors which are crucial to the mathematical model of energy burden, which are income, health status, single parent households, low building quality. This was used from crowdsourced data from 311 calls, and percentage of housing units which uses alternate source of energy as primary source of heating, such as coal, wood, and other non-electric measures. Diesel particulate matter in air. We were using DM 2.5 and diesel particulate matter here in air, which was model data as a proxy for air pollution, because literature says that there is a connection of air pollution and energy burden. So we wanted to check that. And this is last one is average summer land surface temperature, which is used as a proxy for UHI. So how do these vary spatially? And we found out that health and home house heating fuel is universal. Other factors in the spatial regression are local. That means it changes from a census tract to census tract, but health and fuel usage is universal. It is same in all the census tracts in Baltimore City. And these are the linear relationships that we have found out. As income increases, energy burden decreases, which was predictable. As low health status increases, energy burden increases. As single parent households increases, energy burden increases. And as percentage of low building increases, energy burden increases. As alternate fuel use, in a census tract which has high number of coal or wood-based house heating, energy burden tend to be higher. DPM increases, energy burden decreases, which was little surprising. We couldn't find any evidences in the literature. It could be due to the effect of UHI, or it could be due to the fact that people have access to cars, or there was no direct relationship with energy burning. Another factor is land surface temperature. Yeah. So coming to the results, health is most crucial factor, and income comes the second, and the third factor is building quality, which consists of architecture quality and fuel use. So you can see these highly affected neighborhoods. It's mainly health, income, and architecture quality. So architecture quality is like we are measuring presence of bugs, or like is there leakage in the envelope. All these factors act as a proxy for bad architecture quality. So these are the three important factors that affect these neighborhoods. So it becomes like a nexus of three factors. So in order to fight energy poverty, we have to look at all three factors together. Even though in weatherization request form, there's like how people consider paying for health or for energy, but however, there is no concrete emphasis on health status in weatherization policy that should come in because the effect of health on energy poverty in Baltimore City. And also we looked at the mapping, how it correlates with energy poverty clusters right now compared to the past. So the spatial correlation exists, and fuel use. So the gas-based, wood-based, coal-based homes tend to be having higher energy burden, maybe due to the fact that they are older houses and they're using older mechanics. And we found out that social vulnerability, such as single parent households, like here, these neighborhoods, incomes comes after single parent households, that the social vulnerability comes after that. So we have to look at energy poverty, not just from an income perspective, also from a social perspective. These are some policy implications, which I already talked about. So looking at weatherization from also a health point of view, rethinking weatherization qualification, not only based on income, also based on social vulnerability, and upgrading the fuel system. Thank you. Any questions?
So this map here, the West Baltimore shows up as a area, not East Baltimore.
Yeah.
So what's the factor? What's the difference between? I mean, they have, if you look at their income, most, it's two wings of the butterfly.
Right.
So you look at things like that, they show up equally, but they're not showing up on this energy burden.
Right.
What aspect of energy burden means that the east is doing better than the west?
Maybe the income levels are higher, or they have better architecture. Right now, what I see from here, so these are the neighborhoods which come under what you're questioning, right? So,
Yeah, so it's one's green and one's purple. What's the difference?
okay, so the purple means that these neighborhoods are highly impacted by health condition of the occupants. So if they're having like diseases, repeated diseases, that means that most of their income is going to like health related expenses. They can't pay the energy use.
So it's meaning the purple and the purple
So that is DPM level, that is the diesel particulate matter in air. So that could be due to the fact that there is a lot of trucks coming here through this area. And there is also industries here, and also the harbor area contributes to the DPM level in air. Yeah, but it's generally a cold spot as per spatial clustering. So yeah, more attention should be the red box. Yeah.
Thanks for the presentation.
Hmm.
I was wondering on one of your graphs, maps, you showed something about gentrification. I was wondering how it was measured.
How will that matter?
How is it measured?
How is it measured? So the studies. Oh yeah. So she was asking about gentrification. What are the factors for the qualification of gentrified census tract? So the study that I was looking at, they measured. I think they measured 3 factors. The education level of those, change in education level of those census tract, median income level increase. I forgot the third factor. But if you look at the study,
What's usually housing price?
yeah,
Housing price.
yeah. So if you look at the third source, which is by NCRC, I guess. Yeah. So they have some qualifications which they classify if there's gentrified or not.
So we have to proceed into the next presentation. Thank you so much, Arjun.
Okay. Am I audible to everybody?
Yes, you can share now. Could you
Okay.
try sharing? It's not-
Okay.
Very good. Please proceed.
Hello, everyone. I'm Rosina Adhikari, a PhD student in Department of Architectural Engineering, Penn State, working with Professor Wang Dachuo on studying energy efficiency and climate resiliency of row houses in Baltimore City. So the overall motivation behind this work is to understand how we can prepare Baltimore City's buildings for a net zero carbon future, also while making those buildings more resilient towards extreme weather such as heat waves. Our research scopes starts from buildings level. This is a bottom-up approach where we start from buildings to communities to the cities. But at this stage, we are focusing on building scale to understand the behavior of each type of buildings in different scenarios and find the technology solutions that will enhance both energy efficiency and climate resiliency. We started by collecting a lot of building characteristic data, such as building type, fuel type, heating system type throughout the Baltimore City, and translated those into representative archetype energy models. At the same time, we are also working with utility companies to get, with BZ, to get the metered energy use data to calibrate our archetype model. This is the general framework. And then for the building characteristic data, we have been using property tax database as well as other real estate property database. One of the prominent architecture in Baltimore City, as we all know, is row houses, which consists about 52% of existing housing stock and carries a lot of historical and architectural significance. These have multiple overlaps with multifamily units as well as single-family detached houses, but row houses or single-family attached houses in general have been largely overlooked in building research. So we started by developing a representative building energy model of row houses in Baltimore City. For this, we collected a typical characteristic of Baltimore City's row houses. We want to represent the statistical representative characteristic. So geometry, envelope, and HVAC systems of row houses in Baltimore City to translate those into representative energy models of end units and interior units. After that, we compared the performance or prediction from our models with the building performance database, which is a benchmark data. Comparing with this, as you can see in the plot, the median of the building performance database closely aligns with the prediction of our interior unit model, and the end unit also lies in a reasonable range within the distribution. So after verifying the performance of our model, we proceeded with the energy efficient retrofitting study. For this, we considered our baseline model, which is the model I just discussed about, and retrofitted it to recent energy efficiency standard IECC 2021. And studying the energy saving potential out of that retrofit, we can see a huge energy saving potential. And we can also see a clear, like the end unit clearly has a higher energy consumption as well as higher energy saving potential than the interior units of row houses. However, these energy efficiency measures or codes do not were developed by keeping energy efficiency in mind, energy consumption reduction in mind, not necessarily thermal resiliency. Thermal resiliency is like building's ability to maintain a comfortable and safe indoor environment during extreme weather events or power outages or system failure. This becomes more and more important as we are seeing the climate change and its consequences. So in this study, we are trying to see how upgrading our buildings to recent energy efficiency standard will impact the thermal resiliency of those buildings. So the first study is to see how these houses will behave without HVAC system when upgraded to a recent energy efficiency standard. In formal term, it is called thermal autonomy. So as you can see in the figure, the blue region indicates two cold regions, which is decreased by retrofitting to recent energy efficiency codes. However, the two hot region indicated by this red region is actually increased during the summertime, which means there's more risk of overheating the building when sealing the building or making the envelopes more tight. So there's clearly a necessity to include the concept of thermal resiliency into energy efficiency standard before retrofitting our buildings. Another indicator is passive habitability indicator, which indicates how long an indoor space can remain habitable after a prolonged power outage. For this study, we are using three kinds of extreme weeks: the typical extreme week, historical extreme week, and future extreme week, to simulate a 7-day power outage scenario. The extreme week is generally the week with highest average daily minimum temperature. And with this, we'll measure the uninhabitable degree hours in terms of standard effective temperature. From the results we have so far for the typical extreme week, we can see that the interior units shown in this interior parts of the plot can maintain the habitable environment long time after the power outage as well. So they are more resilient to the extreme climate event. However, the end units violate the resiliency criteria sooner than the interior unit, posing a larger threat of thermal stress to the occupants inside end units. And also we can notice that the retrofitted building actually perform worse in some cases, in case of thermal resiliency or in case of extreme weak power outages than the baseline unit, which means with this we can conclude that the energy efficiency measures do not necessarily equate to the thermal resiliency measures, and also the end units or end unit row houses are at higher risk of energy burden due to energy inefficiency, as well as thermal stress due to the problem of overheating. That's why when devising strategies or incentives to retrofit these houses, there should be a consideration of these factors. And moving further, we still have some work in the buildings level where we will be finding out the building technology solutions that are both energy efficient as well as thermal resilient. And then with the building stock data that we have and the archetype models that will generate, we'll move to the community scale where we will devise neighborhood level strategies for resiliency during extreme heat. And with the insights from these two levels, we'll see how city can formulate energy efficiency and resiliency policies to serve all kinds of communities and the threats of extreme weather. This is how we envision the climate resilient and equitable decarbonization pathways for the buildings of Baltimore City. These are some published and on progress work that will soon be delivered. And if you want to learn more about the research or connect for any kind of collaboration, please feel free to contact me. If you have any questions, I'm ready to answer. Thank you.
Thank you so much, Rosina. Any question for her? Yes, please.
Is it possible using this model or maybe something else from the Buildings and Energy Group to get an estimate or a sense of the anthropogenic heat flux out of the building?
So, Rosina, the question is that, is it possible to use these models, the energy models, for anthropogenic heat fluxes out of beyond the buildings, basically?
Into the atmosphere.
Into the
Do you
atmosphere.
mean from buildings to atmosphere, right?
Yeah.
From the envelope of buildings.
Yes.
I think, I mean, so far I need to look into this further for sure, but from my knowledge so far, it should be possible, yes. But the Energy Plus models are like 1D representation of each surface. So you would not have detailed heat flux from very fine resolution, but definitely from like building each surface is facing each orientation, we can calculate that.
One challenge that with the energy models that we feel is that oftentimes we don't have the material, the cladding material characteristics of the existing neighborhoods. So we could have it based on the pictures, but if you want to build it based on a larger scale, probably you don't have those. But any other
initial estimate, like you said, it might be possible though. Please feel free to email. I cannot see who is questioning, so
Ben
I have
was
an email
asking.
address there. We can talk more. Sure.
All right. Thank you. Other questions? All
I
right.
had a question on the, oh, go ahead.
Please proceed.
Yeah, I had a question on the building stock data. How often is that updated?
Do you mean
When you moving forward, you said you were gonna begin to pull in building stock data. I just was curious of how frequently the building stock data is updated. Right, it's not changing that much, but it is changing across time. So I just was curious if we could get like a current stock.
I think, yeah, that is a huge challenge. We are using two data sources. One is tax assessment data source, which should be updated annually, but not very trustworthy since it largely depends on occupants' knowledge about the buildings itself. Another we are looking for is the real estate, like housing, the real estate market listing database, which is fairly updated whenever the house is in market, and there are multiple listing services that work on updating those on a regular basis, which is a bit more reliable than the tax assessment database and has more finer details, but still there's no accurate answer to how frequent it is updated or is it the most recent.
Okay, no, that makes sense. It's a tough topic. Thank you. Great talk.
Oh,
Can I just see slide number 17 again? I was just trying to take some notes.
Could you show us the slide number 17?
Okay,
Just really
sure.
quick.
Sure.
Okay. Got it. Thank you.
Very good. Oh, thank you
you.
so much. We need to proceed to the next presentation. Rawat?
Okay, I'll stop my share. Thank you, everyone.
Thank you, Rasmi. Wonder if I find your presentation. It's here. Right. Oh, no.
Okay, hi everyone. I'm Rawad Al-Kuntar. I'm a research engineer at NREL and also a PhD candidate at Georgia Tech University. And I will be talking about a framework to characterize bottom-up urban energy models. So basically, the topic is if we have few known information about the characteristics of the building and unknown data, so how can we predict these unknown characteristics? And for this work, I'm collaborating with I work with my colleagues, Jiazan, Q, and Hannah from NREL. So first, I'm going to give you a very quick introduction about UrbanOpt and ResTalk, which are models that are developed at NREL, and then introduce the general framework.
Because you have to respect them. You have to be a good quiet.
If you could turn up the volume, that would be great. If you could mute yourself, please. Okay, so I will introduce UrbanOpt ResTalk tools from NREL quick, and then discuss the general framework and the methods for predicting and disaggregation methodology for predicting unknown characteristics, and discuss some of the results. So first of all, UrbanOpt is analytics tool for modeling communities and urban districts. This is developed at NREL, and it is built on top of the DOE open sources like Energy Plus and OpenStudio. And as you can see here, UrbanOpt is the SDK, which is the underlying analytics. It's not an end user interface, and we collaborate with companies in order to it can be integrated into end user interfaces for tool users to answer questions for different clients. So here I'm gonna walk you through workflow of the analysis workflow of UrbanOpt. So we have building footprint data that we gather from different resources and geometries, and then we combine this geometric information with non-geometric data like building attributes like the building type, the HVAC system types, the properties of the envelope, etc., in order to create a baseline model. And then with UrbanOpt, we can the core capabilities, we can create different scenarios and analyze the results. So within the UrbanOpt platform, we have three different modules. First is the building core component modules in order to model like the building systems and their interactions. And then we have the grid interactive modules where we can model distributed energy resources like PVs and batteries using GREOP, and also modeling the grid systems, substation, transformers, and the line that connect to the buildings. And this is using OpenDSS and DITTO and RNN reference network model. And also we have a third module, which is modeling shared thermal systems like heating and shared heating and cooling thermal systems. So this is UrbanOpt is the second tool I'm going to use is ResTalk, which is more at modeling the building stock in the US. So for ResTalk, we gather data from a lot of resources, and it include data about all the characteristics in all the states. And these are like probability distributions at the resolution of a PUMA or census tract. And then we sample from this data in order to create models for the different locations in the US. So to show you the differences here, the UrbanOpt, the resolution is you model specific locations, co-located buildings, and define their properties. While ResTalk, we have probability distributions about the characteristics at the PUMA scale, which is the lowest resolution, and then we are sampling from these characteristics to do the models. So the idea here, we want to characterize the inputs for our energy models. And to do this, we are starting with UrbanOpt, but we have here few information that we can know. So for example, from the geometry, we can get from OpenStreetMap, some other properties we can get from Zillow, Redfin, and Microsoft building footprint data. So we have top level information like building type, floor area, number of stories. Sometimes we have the vintage or the type of the HVAC system, but we have a few known characteristics. And the goal here is try to figure out what are the unknown characteristics when we are trying to model at a co-located building scale. So this is from the urban opt side. So what we are doing here is we're trying to connect to the rest of data set and disaggregate the data in order to predict the unknown characteristics. So rest of data set have much more data about much more characteristics like the HVAC system type, the insulation, infiltration, and also some information about the income, the number of occupant, and the behaviors of occupancy at this PUMA resolution. So we did this aggregation framework in order to connect these two and extend the urban opt with these build stock inputs and data. And then we integrated them into the urban opt model. So here I'm gonna just to show you an example. So basically you have a building ID and then you can we need to predict, you know some of these characteristics and we want to predict all the unknown characteristics from these characteristics for the buildings. So I'm gonna discuss the disaggregation workflow that we developed. So first we are from the characteristics we are doing sensitivity analysis in order to know what is the most important characteristics. And then we develop two methods. First method is when we get a new building with some unknown characteristics, we are trying to find the nearest neighbor from the rest of data set and doing imputation techniques in order to predict the characteristics. And the other model is a neural network model to predict these characteristics. And then we're doing validation. So first, here I'm going to show the sensitivity analysis example results. So you can see here, after doing the sensitivity analysis, you see that the building, for example, for this location, the building type, floor area, heating, fuel, insulation, like are the most important, and so on. So we are using this sensitivity analysis in order to do a weighted KNN, K nearest neighbor approach, where we get the blue is the new building that comes with specific known information and missing data. And we are trying to find the nearest neighbors of the rest of data set to this building using the weighted KNN. And then from the nearest neighbors, we are doing imputation techniques in order to predict the other characteristics. So this is one of the methodologies that we developed. The other methodology is a neural network model where we know few inputs, characteristics, and we're trying to predict the unknown characteristics. So we train a model within this data set and utilize this model in order to predict the unknown characteristics. So for the validation, we are, for example, here, I'm going to walk you very fast through this. So we have the rest of data set, all of these properties. And then when we know few information like building type, floor area, number of stories, we are masking the other information. And we're trying to predict these information and then compare the results. So here I'm going to show you just fast some of the results. This is using the method so we can predict the categorical variables characteristics with a good accuracy from the KNN approach. And then here what we can do now is every time we have different levels of data. So let's say we have the first iteration, we know these data, but then we know the heating fuel, then we know the vintage, then we know the occupants or the income. So the accuracy will increase as when you know more initial known characteristics about the buildings. And here, this is comparing the results from the KNN imputation model that we developed and the neural network model. And as you can see, the KNN approach also perform as good as the neural network model. The neural network model performs a bit better, but it takes more computational time to train and to train the model. So that's basically the presentation. Questions?
Thank you so much for the presentation. I'm wondering, have you done any kind of review of Baltimore's housing stock to see how this could be engaged?
So the question was if we did any review about the Baltimore building stock to utilize this framework there. This is the next step. Basically, now we are trying to build up a case study in Baltimore and utilize. We are gathering the rest of data for pumas in Baltimore area and utilizing this data set in order to characterize the model. What I presented here is just the approach that can be applied in any state, basically. But next step is we're gonna apply this approach to predict unknown characteristics for buildings in Baltimore. Thank you.
Follow-up question to that. That's excellent. I think that'd be a very good advantage to see how the model interacts with the nuances of Baltimore city housing stock or building stock. Question. You're pulling data from GIS, and I'm trying to understand, yeah? You're pulling data from GIS, from the CAD drawings of a particular city, from the city authorities. What other data sets are you pulling from in order to create this model?
Yeah, so there's the question was, what are the data sets being pulled to create these models? And there are many data sets. So basically, from co-located buildings, we get from OpenStreetMap for the geometry. There is the Microsoft building footprint data. These are public sources for geometric data. We have, again, from Zillow, Redfin, you can get few information about the characteristics. And then for there is surveys, of course, for unknown for other characteristics. At Enrel a few years ago, ResTalk dataset was developed, which is I'll send you a link for this. There's a lot of free sources for this data set from the American Time of Use data, other resources, surveys at the census tract level. So they gathered a lot of information about the buildings, but this is a probability distribution at this scale. So we are utilizing both of these in order to do a more accurate prediction or characterization of our models.
So I think it would be really, really helpful for the building envelope group to have a list of all of the data sets that this particular framework engages, so that we can identify from the city of Baltimore perspective if there are additional that could be engaged and that ask you whether those data sets can be harvested. So a comprehensive list of what you are using right now for this modeling. And then we can kind of test it against what we have. Thank you.
So you mentioned about KNN clustering. So are you using any spatial weights to that?
Yes, so we did. So the question was about the KNN approach and if we're using any weights.
Spatial weights.
Spatial weights. So basically, the sensitivity analyses are based on the characteristics. And we use this to make a weighted KNN. But the characteristics are building characteristics, not that spatial, but I think this is a good idea to include.
Yeah, because similar typologies tend to cluster together.
Tend to cluster, together in specific areas.
Good response.
Thank you.
Well, thank you so much. Next presentation, Alex and Warsaw, please.
Good afternoon, everyone. My name is Alex Morphy. Good afternoon, everyone. My name is Alex Morphy. So I'm working on green buildings and how it affects climate change. My topic is the comparative analysis of climate adaptive features in green buildings in Baltimore compared to DC. So the reason why I this topic There are two cities separated by just 35 miles, being so different. Yeah, so we are trying to analyze it on, okay, there are a few basics, touch that, presentation. Yeah. But first of all, an overview of Baltimore. Baltimore has a population of over 556,000 people. Most of them are African Americans. And housing stock, most of Baltimore's homes, they are traditional row homes from the 19th century. And these outdated buildings, they contribute to 60% of the city's emissions. Revitalization efforts are needed in the city. So the LEED certified building stands over its 400, it stands at over 400 buildings in Baltimore, of which some are pre-certified. Yeah, as we see here. So looking at this is Baltimore got certified LEED, certified for cities last year, 2023. So when you look at the scorecard here, integrated process is good, the natural system and ecology is good, the transportation is okay, the water efficiency seems okay. So the Baltimore green building, this data is basically on the green buildings, only not on the Baltimore housing stock. This is on the Baltimore green building. So this is 22. So this is excellent, because when you say green buildings, first of all, okay, I have certification in Envision and LEED, but Envision focuses more on like that's from the Institute of Infrastructure. So that focuses more on infrastructure like bridges and others. But with LEED, that focuses more on like green buildings, homes, motorized homes. Yeah, so looking at this now, look at the low areas where is lacking. So material and resource, that's one. As I said, the first slide said most of the buildings are from the 19th and 20th century. So when we want to, let's say when a building is demolished and you want to maybe use some parts, some of the parts are always not going to be good enough. That's why this is low. And Baltimore is very much in the early stages of the green building implementation. And also there's the quality of life. Yeah, with what the green building offers, and also the problem we have, which are the vacant homes. So it's like a fight between both of them. We have over 13,000 that affects 20,000 vacant lots. And the the LEED buildings in Baltimore stands at just 400, of which 195 are still at pre-certified stage. So looking here, we have 32 LEED certified buildings, 106 silver, 102 gold, 11 platinum. So when you say a building, first of all, LEED stands for Leadership in Energy and Environmental Design. When you say a building, for it to be certified LEED, we have a few credit category points, and of all the category points, the energy and efficiency stands at the highest at 33. So looking at this to get easy points, and when you say it's a building in silver, so it will have taken a lot of points from the energy credit category. So this is good to go. The green, like integrity of the building, like you can see it's good. Yeah, from silver to platinum, not focusing on the certified. Okay, so we have 137 new construction projects for 3 core and shell, just 1 warehouse, 130 residential buildings, 23 residential centers, 44 educational institutions. As you can see here, there's no healthcare yet, although we still have 4 that are pre-certified compared to Washington, DC, because as I said earlier, these 2 areas are just separated by 35 miles, yet so different. Looking at this, so we have new construction. This presentation is focused more on Baltimore, so the data for DC omitted in some areas. So all of this. Okay. Baltimore still in the early stage of implementation, limited number of LEED certified buildings, higher greenhouse gases due to reliance on coal and nuclear energy compared to DC, that's where we're advanced. Okay, so this is the focus area on how green buildings affect the effect of green buildings in the neighborhood in Baltimore. But for this presentation, I'll be focusing more on the environmental and socioeconomic factors. Okay, so this is the environmental. First of all, Maryland has the nation's highest rate of death from air pollution. Based on the 2013 MIT report, Baltimore's air pollution kills at the rate of 133 per 100,000 people. Also, we have the LEED exposure and also health impact from blighted properties. Because remember what I said, because of the date of the buildings, you can't use them. You can't use most of those parts for the new green buildings. Okay, I have the precipitation here, and Maryland. So over here, yeah. Yeah, so it's heavier plus 10%. Yeah, heat days. So this is heat wave days in Baltimore where heat index is above 105. Here, we should be within here, so it should be around here. So maybe at 25 for now, but 2050, we're looking at 47, with it growing compared to Mississippi, that's very hot. Okay, so a brief focus for this is the Broadway East neighborhood. 90% of people there live, 90% of people of color live there, 50% live in poverty. And as you can see here, there are no green buildings here. And sometimes you ask yourself, what is the importance of these green buildings? What's the implication of having a green building in an area? All of that will be answered here. Okay, so this is what this area looks like. There's no green building here, almost no green infrastructure here. So this is basically what it looks like. Okay, so we come to LEED. Okay, so I say green buildings, yes, but when I say green buildings, I mean LEED, because LEED kind of sets the standard for green buildings. And Vision is more, as I said, for infrastructure. So this is the world's most widely used green building rating system. LEED certification provides a framework for healthy, highly efficient, cost-saving green buildings with environmental, social, and governance benefits. Looking here, this is our rating system. So for this project, most of the comparison I used was based on the building design and construction, not interior design and construction, because for the interior design and construction, it's not really concerned with the neighborhood, just what it offers to the people that live in that current building. So, and when you ask, like, the basic difference between a green building and a normal traditional row home, as we see in Baltimore. So these credit categories are what spells it out, because for a building to be green, first of all, the sustainability initiative is needed. Integrative approach, this is where you bring everyone in, even the people not involved directly, everyone in, locating your building in good surrounding area and diverse areas that prevents transportation between places. Material and resource, as I said, Baltimore is very low on this because of how old and outdated the buildings are. Water efficiency, energy and atmosphere, sustainable site, indoor environmental quality, innovation, and regional priorities. Okay, and as I said, for this presentation, I tried to not use the certified buildings because, yes, LEED compared to other platforms, it is, there are points that are you can easily attain a few points from LEED. So I try not to concern myself with this certified, but from silver, any building that stands at silver to platinum. Okay, I'll get it. If it starts from silver to platinum, so since energy and efficiency has 33% among the 100%, 110, but it's capped at 100%. So any building that is at silver is certified, is good to go as energy is concerned. Okay, so this is what a green building offers you. You have trees, you have solar panels. This, talking about energy, one good thing with green buildings is their involvement in demand response, where they produce more. Sometimes when they produce more than enough energy needed, you can even send back to the grid. You have VOC, low VOC, that's for indoor environmental quality. You have the dehumanizer system, that's for the MEV rating, depending if you have pets, for smokers, and for allergies. Yeah, okay, so for this presentation, I tried to not concern myself with the building, more like the clusters, as you saw earlier. Okay, so this is what it means to have a green building in an area, the implication. So this is the George Washington University. Okay, so this is, you have the trees, you have your bioswales here, you have your bicycle lanes over here that connects it to everywhere within diverse areas surrounding their city. So you have your park just close to it here. And placing a building next to a green building also draws points from the green building you placed it next to. That's how LEED is designed. Okay, so at environmental stage, okay, so hazardous waste proximity, site selection management, material and resource, indoor environmental quality. These are the factors that are in place to, let me just go to, First of all, okay, as I said, I'm talking about not just what the building can do, but what a cluster of green buildings can do. So this is superfund proximity. You get more points using when you place a green building in a superfund area. So when you look here, and also the advantage of green buildings is what? An advantageous part of green buildings is what it offers to the neighborhood. So looking at this now, this is where the majority of the cluster is in DC. And look at how it affects the whole neighborhood, superfund proximity, because when you remediate the area, place the green buildings there, that is how it looks. Okay, so compared to Baltimore, yes, we have buildings here, but they are not enough. The green buildings are not enough. Together with the green buildings, there are vacant homes here. So this is what we get basically for Baltimore. Okay. Okay, so lead paint, lead. Okay, for the lead.
If you could just show your last green building, what's that right?
Okay, well, this is basically what I'm saying. The cluster of green buildings there, cluster of green buildings. This is what it looks like. Okay, same as low life expectancy. In an area with a cluster of green buildings, this is what it looks like. Area of low life expectancy, this is what it looks like too. Okay, this socioeconomic. Okay. Okay, so I know the earlier presentation talked about the social butterfly. As you can see here, the cluster of green buildings are more focused in areas, specific areas with white non-Hispanic people, and also we have a few in areas with the Black non-Hispanic people. So a cluster of this cluster here is a case of, okay, what my neighbor has and what I don't have. As you can see in DC, the areas that have the Black people, there are green buildings that they are not enough, but they are still some available compared to Baltimore, where you don't even have any at all. And also there are some specific type of green buildings that we don't even have, like the hospitals. Yeah, so I think this is okay. Okay. But let me just talk about this last one. So as you can see, sorry, as you can see here, okay, these are the number of green buildings compared to the population increase of 4. Baltimore keeps falling, DC keeps increasing. But if we see here in the year 2019, yeah, so with this 4, I kind of saw this as an opportunity for Baltimore to, okay, seize on this opportunity, remediate the area, rejuvenate the vacant buildings, yeah, maybe to get more people in. Yeah, that's it. Okay. Thank you.
So we have time only for one quick question that would need quick answer.
What's the implication of lead in the buildings that makes the material less useful?
Lead paint.
Yeah, is that, could you had said that the materials from our buildings, because they're much older, like 19th and 20th century, is it because you can't, when you do deconstruction, the materials that are taken, you get the impression that it's not as useful. Is it because we have so much lead in the building?
Yeah, but the lead is, yeah, you could say that that's just a branch of it, but the lead is mostly, that is talked about in the healthcare system. I know the healthcare completely eradicates lead for it to not be in the building at all, but lead, yeah, that's one of it. I know we have plenty, and if you talk about lead, I would say, yes, that's one of it. So kicking that out. Also, the building materials sometimes, concrete. Yeah, I know we do use that, but no, as for the green buildings, it's not as much as it is in the traditional conventional building.
Okay. Yeah. So it's a small percentage of why the materials are.
Yeah.
Got it.
Well, thank you so much, Alex. If you have any questions, please reach out to us. And if you have ideas for collaboration, please reach out to us and let us know. Thank you so much.
We convene at 1:30.
We need. Yeah.
We'll be here when we.
That's better. Okay, cool. Are we on Zoom yet? I don't think we're on Zoom right now. How can we enter Zoom?
What are you breaking?
Yeah, that's what we're trying to do, break it. Just trying to look for how to get into Zoom. How do we get into Zoom? Oh, I thought you said you were gonna.
No, I didn't. Zoom's already.
Oh, you didn't,
Hey,
okay.
touch on this.
is here.
Yes, touch on this.
Oh.
There it is. So being wasn't sure, so we just left it.
Okay, cool. Excellent. Now we just need the health. section. This is the source.
And it's just one, and I've just got one, everything that I've got is in one file. The health. It should be already
okay.
open. The
Oh, okay.
PowerPoint, I think.
Cool, good. Yes, all right, got it.
Still not wanting to lose this money to Mike, so.
We're just gonna give a brief intro and then Bianca will go. Okay, perfect.
We still need to share the screen on Zoom, Ali. Thank you.
That seemed like looks like the right view on Zoom. Oh, great.
That's good.
Yeah, I think it is.
Self-introduction.
Okay.
Take it away.
Welcome back from lunch. My name is Meredith McCormick. I'm a pulmonologist, so and my areas of interest are asthma and COPD, as well as how the environment affects people with those conditions.
Kirsten Cole, I'm a professor in environmental health and engineering, interested in air pollution and how it affects health.
And so we collaborate together on lots of projects, including this one, which we'll be talking about today. And I cut this out of the grant just to remind ourselves sort of where we started from, thinking about the intersection between climate and health. And one of the things we proposed was to start by thinking about asthma and COPD, two of the more common chronic respiratory conditions, and thinking about factors including temperature, urban air pollution, and then other factors in communities that might impact these exposures and how they influence health. And just, we're going to describe some work where we really are starting with asthma and why asthma. Asthma is really a local problem as well as a problem nationally. It affects 25 million people, including 6 million children. And nearly half of those people have had an asthma attack in the past year. It accounts for a significant number of missed work days for adults, missed school days for children. And it's also a condition that is marked by health disparities, with African-American individuals being much more likely to have asthma exacerbations, to be hospitalized, or to die from their asthma. We're specifically concerned about this in Baltimore City, where the prevalence of asthma among children is more than double the national average. And our center and a lot of our collaborative work focuses on environmental health disparities driving these exacerbation rates. And one of the things that we know related to asthma as well as other health conditions is that where we live matters. And on the left is a map of the historic redlining practices, discriminatory lending practices in Baltimore City. And here on the right, we see a map of asthma, childhood asthma rates, hospitalizations in Baltimore City. And as we're going through our work, we'll be tagging back to maps and looking at different risk factors and exposures. And this is just a high level introduction. We also know that where we live matters in the sense of our likelihood of being exposed to outdoor air pollution differs based on our neighborhood, as well as the composition of neighborhoods. And this is an annual report that's put out by the American Lung Association, and the most recent report described that people of color are almost 4 times more likely than white individuals to live in an area with failing rates for air pollution.
So linking all this back to BSEC, I think there's a lot of interactions between the research that we've done in the past, what we're doing for BSEC, and a number of the working groups within BSEC. So one area Bianca will talk about today is characterizing an urban heat island. And we have also complementary studies looking at interventions for urban heat islands. So really thinking about, during the summer months, what can we say about, assessing temperature and sometimes humidity at high spatial resolution with sensors. Can satellite products be used to help understand these relationships? And then are there interventions that could be used to benefit some of these communities that have a forest urban heat island? And this is, I think, especially important as we think about particularly susceptible individuals and in some of the neighborhoods in Baltimore. This is data from a paper from a while ago, but with Darren looking at indoor temperatures. And so you can see outdoors in the green line, hot during the day, cool at night. But in some households where people didn't have air conditioning, you can see, or let's start with people with, central air conditioning, keeping the temperatures reasonable, and most of the time in the blue trace, just a room, air conditioning, not doing as well, but still not getting as hot as it is outdoors. But for households without air conditioning, and in some places where people may not feel comfortable opening the windows even at night when it cools down, the temperatures could stay extremely warm. So this is for an entire week, indoor temperatures above 90 degrees. So you can imagine, not great probably for anybody, but particularly for elderly people who may have temperature regulation controls. This can pose a real concern.
And so today, this is a conceptual model that we're using really as a starting point, I think as a demonstration of, and this is a conceptual model that we've built thinking about all the things that might impact asthma. And you can imagine a similar schematic for COPD. And we're really focusing today over here on the left in the environmental drivers of morbidity. And I wanted to also just introduce the large team that we're representing today, and we'll have Bianca online and Emily presenting their work. They're both striving towards their PhDs, and we'll be talking about how this relates to their own personal goals. We have other trainees in the Department of Medicine and really and our collaborators from Penn State. And so just an overview of all of the individuals who are working on this project. And with that, I'll turn it over to Bianca, who is online. I'll stay through your.
Hi, everyone. Can you hear me?
Yeah, you sound good.
Okay, cool.
All right, Bianca, you can start.
Great. Okay. All right. Hi, everyone. My name is Bianca Cruz, and I am a PhD student in the Earth and Planetary Sciences Department.
You're very quiet, Bianca. I'm not sure why.
Okay.
Might be us, might be you.
Bianca, can you keep talking, please?
Yeah, is this better?
Oh, yeah.
Yeah, that was
Okay,
our
great. Sorry.
fault. No, it's our fault.
You're good.
Okay, great. Hi, everyone. My name is Bianca Cruz, and I'm a PhD student in the Earth and Planetary Sciences Department at Johns Hopkins. And I'm happy to present some of the research I've been working on at the intersection of heat and health. So today, the title of today's presentation is Harmonizing High Resolution Earth Observation and Health Data to Examine Associations Between Extreme Heat and Asthma Exacerbations in Baltimore, Maryland. Next slide. All right, so why are we focusing on asthma? Meredith touched on this a bit, but I've included a few stats here to highlight this point. Notably, Baltimore City has the highest rate of emergency department visits due to asthma in the entire state of Maryland. And lastly, as many of us know, over the years, the resolution of satellite and climate data has improved. However, there have been limitations. Oh gosh. With the available health data that we're able to use. But in this research, we're able to address this challenge by using the high resolution asthma data available through JHU PIMCO, which Meredith and Kirsten just talked about earlier. Next slide. All right, so before we get into the health data, I'm going to first draw our attention to the heat data I'll be using. So we obtained the heat data for this study by creating urban heat island models, which use a ground-based network of iButtons, satellite data, and National Weather Service station data. And on the left, you can see an image of an iButton and its shields. In the middle, you can see where the iButtons were placed throughout the summer. And on the right, I've just included a few images of some satellite derived data that we used here. Next slide. Cool. So in case you're interested in the satellite and National Weather Service Station data that we used in our models, I've listed them here. We actually created two models, one to predict the nighttime urban heat island and another to predict the daytime urban heat island. Next slide. Cool. So we specifically used generalized additive models to account for all of the variables we included in the models. And we found that they predicted both maximum and minimum air temperature anomalies quite well. And these anomalies are relative to the National Weather Service Station at BWI. So on the left, you can see the minimum temperature anomaly maps, which are daily, and that represents the nighttime urban heat island. And on the right-hand side, you can see the maximum temperature anomaly maps, which represent the daytime urban heat island. Next slide, please. Cool. So using these models, we were able to predict both minimum and maximum air temperatures for subsequent years. So 2016 to 2022. And actually the summer months of June, July, and August from 2016 to 2022, that's the study period for this heat and health, specifically asthma research project that I am discussing with you all today. Next slide, please. All right, so now that we have those maps, well, what can they be used for? They can be used for numerous things. First, they can identify areas throughout the city which experience warmer air temperatures than others. They can also be used by local government officials and community groups to help develop and advocate for heat mitigation and adaptation strategies. Now, moving into the heat and health project, now we can also merge these data with the high resolution health data from JHU PIMCO to better understand how extreme heat affects asthma exacerbation rates. Next slide. So that's what we did. We integrated medical health records with environmental variables. And this flow chart here is meant to demonstrate this. So we can start from the bottom left and you can see the address level patient data, which were aggregated up to the census block group and census tract. And then on the top left, those are the satellite data, which were also aggregated to the census block group and census tract. Below that are the high resolution air temperature maps, which are also aggregated to the census block group and census tract. And we also included National Weather Service Station temperature data because I'm interested in looking at the various types and resolutions of Earth observation data, which I will touch on in a second. So all of these data were all merged together according to their respective geo IDs. Next slide, please. Cool. So now that we know how the data were brought together, we can now bring up the research questions. So the proposed research will answer the following questions. One, what is the benefit of understanding the association between temperature and asthma exacerbation at various spatial resolutions? Two, what type of resolution of Earth observation data can adequately capture delayed effects of extreme heat? So to study the relationship between heat and asthma, there are two common methodologies, the first one being the case crossover design, and the second being a time series analysis. And when we talk about the data that are typically used for these, in terms of environmental data, they're from the nearest weather station. So in our case, it'd be from BWI. And in terms of asthma exacerbation data, oftentimes they're aggregated to the city level. So there's a star next to case crossover design, and that's because that's the approach I'm currently working on. So taking a sneak peek into the data, I've included maps here of asthma exacerbation counts for both adult and pediatric patients. So within our study period, again, June, July, August, 2016 to 22, there were 819 asthma exacerbations for adult patients and 695 in pediatric patients. Cool. So here are some preliminary results of the conditional logistic regressions, which are single lag models with lives of 0 to 14. And so A lag of 0 would correspond to the day that the patient visited the emergency department. A lag of 1 would be the day before the patient visited the emergency department, and lags go up to 14, which would be 2 weeks before. So starting off with pediatric patients first, looking at the model on the left-hand side of this, this slide, which use the 1 meter air temperature data, we find that there's a higher risk of asthma exacerbations on warmer nights than on warmer days, up to a week before an emergency department visit, which is what we would expect to see in terms of the nighttime temperatures. And if we're going to look on the right-hand side, where we use the National Weather Service Station air temperature data, which is coarse, we don't really see this pattern, and find that warm nights that were experienced more than a week before an emergency department visit corresponds to a higher risk of asthma exacerbations. And you can see that when we look at lags 10 to 14. Next slide, please. All right, so in adult patients, we don't really see the same distinct pattern that we just saw in the pediatric patients, but we generally see a higher risk of having asthma exacerbation on warm nights. But if we focus our attention to the right-hand side where we use the National Weather Service Station air temperature data, we find that adults have a higher risk of asthma exacerbations on warm days. Well, on the day they came into the emergency department visit when the day is hot, and the day before when it is also hot. Next slide, please. Okay, so ending on next steps, there are many things that I need to do, but I didn't want to provide you all with my to-do list. But at the moment, these models are single lag models, so I hope to include covariates into the model, especially now that we know they work. I also plan on conducting analyses using different temperature data at various spatial scales. And lastly, I hope to move on from, not move on from, but also include looking at extreme heat events rather than a continuous daily air temperature. Next slide, please. Oh, is that it? Okay, cool. And that is it, and I'm happy to take any questions.
Curious for the model parameters. I could just use some help understanding. But all of the estimates for the lag crossover to 0 line right there, 95% interval. I mean that none of the terms are significant in your findings.
So it wasn't about model parameters, right?
Yeah.
So
Since all the error bars are close to the 0 line, are your differences significant?
No, they're not significant, not statistically significant. If they
That's not a concern that so few of the curves are significant.
is that not a concern that so few of them are significant?
It is a concern. We'll look into it a bit more, but when we look at, generally we kind of see the pattern of higher temperatures during the nighttime for pediatric patients on the 1 meter. That I think that pattern that we see using the higher resolution data is helpful, because when we look at the National Weather Service Station temperature, there's really no difference that we can see until like more than a week before. So we'll need to kind of reiterate and maybe adjust different control windows and kind of manipulate the model a bit to get a clearer picture of this.
So could we go to the I buttons location map? And Bianca, could you speak a little bit more about how or what were the parameters of the location of the I buttons?
So the question was, can you explain about some of the parameters about the locations of the I buttons?
Yeah, so this was before I got here, but they are placed throughout the city. And I know that they initially had a few more, but they had we had removed a few because they were placed on not appropriate stations, such as, you know, a pole or etc. And in terms of where they're placed, I don't know if I can actually explain the location of, or the decision process of why they were placed where they are.
I can answer that. One of the questions was the decay effect of cooling from a park. So the cluster in East Baltimore starts at Patterson Park. And there's an array of buttons that go up the watershed, I think, up to or towards Clifton Park, to see how much cooling effect would influence areas at what distance from the large green space.
So if a part of the town doesn't have green space, it's not monitored?
Well, this was a pilot. If this is referring to the shields that we developed for that, it was a pilot of 100 buttons. Wasn't trying to be comprehensive, it was a test pilot.
Okay. So the test pilot is really collecting data from places that are already.
In between green to not green to green, so let's say green.
So the I button is placed.
I think it was written up by Anna Scott in her urban temperature variability article.
We can talk about this offline. We need to move on for the sake of time. I'm still in the room.
Next up, we have Emily Scott, who'll be talking. I think Bianca and Emily have really nicely complementary focuses in this initiative. And Emily's coming to us from the health side. And I thought I would just mention one more thing, because I realized I didn't exactly set up the construct of the precision medicine initiative, but the institution has made a large investment in precision medicine that sits in the Department of Medicine. And essentially we'll be talking about the precision medicine analytics platform, which is a platform where health data from all patients who've been seen in the Hopkins healthcare system is aggregated, and then other health data is brought into this platform. And as part of this initiative, we've brought in environmental data, which is Bianca's been focusing on that, and Emily will now continue the conversation. Emily Scott. You have to stand. You have to stand for this. Okay. Hi, I'm Emily Scott. I'm a PhD candidate in the Department of Biostatistics at the School of Public Health. And I'll talk about leveraging electronic health record data to study environmental drivers of asthma exacerbation. I'll begin with a brief description of the overall Asthma Precision Medicine Center of Excellence, or PIMCO cohort, before focusing specifically on asthma exacerbations, the spatial and temporal distribution of those, and then linking those to environmental and sociodemographic data, specifically maximum daily temperature, minimum daily temperature, diurnal temperature range, which is just the difference between the max and the min. I'll call that DTR, and also linking to area deprivation index. Then I'll share results from an analysis looking at asthma exacerbations by ADI and DTR, and finish with where we want to go from here. So to start, we have over 500,000 patients in the asthma PIMCO with a diagnosis of asthma or symptoms related to asthma, and a good mix of adults and kids there. So 70% are adults and 30% are kids. Looking at where those patients are coming from, these are maps of Baltimore City, where the lighter blue corresponds to census tracts with fewer patients, the darker blue corresponds to census tracts with a greater number of patients. On the left, we have adult patients. On the right, we have children. And I've added a star where Johns Hopkins Hospital is to help orient you. And then the red line down the middle, that's 83. So more patients coming from East Baltimore than West Baltimore, and just generally more concentrated around the hospital. There are some neighborhoods overlaid on that if it helps sort of orient you. For kids, we also have data coming from Florida, from All Children's Hospital. So that's in Pinellas County. Here's a map of Florida, and I've boxed out Pinellas County and expanded that. Again, I have a star to mark where the hospital is, and similar to Baltimore City, we have more patients sort of surrounding that area. and light blue to dark blue for fewer to more patients. An outcome associated with high morbidity is asthma exacerbations, which can lead to time away from work or school, excess medical